Hello everyone, this lecture of dynamics of the lithosphere will focus on power law creep. This is the second part of lectures on viscosity. In the previous lecture, we have introduced a linear model with a constant viscosity. We were relating the deviatoric stress tau to the deviatoric strain rate here with a coefficient of viscosity. This is a linear flow law. You've plotted linear flow laws for three different viscosities. Here is the stress or deviatoric stress and deviatoric strain rate. And of course, you had lines with different slopes because you were considering different viscosity coefficients. These lines you also plotted in a log-log diagram, and all the lines had the same slope, a slope of 1. Unfortunately, in rocks, so here for example quartz-rich rocks, measurements of these lines can be made. So here you have strain rate and stress on log-log diagram, and I say unfortunately because when the data is plotted into the diagram, the slope is not 1. So here it's closer to 4. So in the log-log diagram, the natural data often yields a slopes larger than 1. To explain this data, we need to introduce another rheological relationship, and that is the power law, flow law. So here we have the strain rate that relates to stress with a coefficient C and an exponent n, which is the power law exponent. These coefficients C and n have to be calibrated by rock deformation experiments. So it turns out that there is a nonlinear relation between stress and strain rate for most rock, and for this we need to use this relation, this power law flow law. This here now is an example of the data plotted on with the same scales here, but for olivine, and you can also see that the lines have a slope different than 1. And in addition, you can even notice on this diagram that experiments made at different temperatures do not coincide on the same line. So there should be an effect of temperature in addition of the power law effect. So in most of the cases, the power law exponent is about 3 for dislocation creep. Diffusion creep and grain size reduction, this can result in an effective stress exponent. This will be discussed at the end of the lecture. The low temperature creep plasticity has an effective stress exponent that depends on temperature and can reach values larger than 6. So what does the power law flow law actually implies? Now we do a similar exercise as you've done in the previous lecture, and we plot stress-strain rate relations for different n values. For n equal 1, you get the straight line as you had last week, but as n increases, the line is curving and bending down. What does this mean? It means that in the case it's linear, the slope of course is constant, the viscosity does not change. If you're here or here, the slope is the same, the viscosity does not change along the line. But if n is larger than 1, the viscosity here is the local slope of this line, and as this line is curved, it means that the viscosity changes. So if you measure the viscosity here, it will be larger than the viscosity being measured there. This is an effective viscosity that varies with the strain rate. So the viscosity effectively decreases with increasing strain rate, and this effect we call strain rate softening, and that's an important effect for all power law materials. So in tectonics, we generally formulate stress as a function of strain rate and viscosity. So we use this generic constitutive law that deviatoric stress is equal to times viscosity coefficient times deviatoric strain rate. The question is how to express eta effective for the power law case. So we need to inject basically this relationship into this one, and we have two possibilities. We can express the effective viscosity coefficient as a function of the stress value, or we can express it as a function of the strain rate values. Both actually work. So the first flavor here is to express effective viscosity as function of stress. So that is the expression you would obtain. So on one side you have viscosity, on the other side you have stress, and the viscosity is 1/2 of c to the power minus 1 tau to the power 1 minus n. Again, these are the material parameters that need to be fitted to experimental data. The second flavor is to compute effective viscosity as a function of the strain rate. So now you have effective viscosity on the left-hand side and the strain rate on the right-hand side. The expression is of course different than the previous one. You have 1/2 of c to the power minus 1 over n, and the strain rate is to the power 1 over n minus 1. So in our exercise, we will assume that a reference stress is obtained for a reference strain rate. So you have tau ref, it will be a given value, and epsilon dot ref will be another given value. And for this, we will constrain the factor c. So we will have to use this relationship to define c in the exercise. I will explain this more when we discuss the exercise. So that's the relationship we want to use. Why does the power law rheology matter in general? So it matters a lot when talking about pinch and swell structures and necking phenomenon. So this is an example of calc silicates that you can observe in the contact areole of the Adamello batholiths in the Alps. And what you see here are strong layers that are necked. So you see it's a pinch and swell structure. To form this type of structure in rocks, it is necessary to have a power law rheology for the materials involved in this deformation. But if you move to the larger scale, the scale of the lithosphere, you know that continental rifting leads to thinning of the lithosphere and potentially opening of seas. The overall structure of a continental rift can be seen or imaged as a necking process too. So you have different layers in the crust and in the lithosphere with different strength. And when you stretch the lithosphere to open the rift, you can develop necking structures. So at the lithosphere scale, the process of necking is also important because it shapes passive margins. So power law is a necessary condition for necking. Thus, power law creep matters for natural structure development from the outcrop scale to the lithosphere scale. So that's for necking, but it also matters for folding. Remember this picture with the magnificent fold structure of the Morkel nap. Folds are seen at the large scale as well as at the small scale. And it turns out that power law rheology matters for folding. So these are results of finite element simulations of single layer folding. So you have a box here with a strong layer in the middle, and this layer is being shortened by 60% in both cases here. What differs between this column and this column is the power law exponent. So if the material is linear, you can predict a fold. But if the material is nonlinear, you create this periodic folding pattern, which is much better expressed and much less layer thickening due to the pure shear. So the power law impacts also folding. So let's recall the diagram for olivine that we saw earlier on. this was log strain rate versus log stress, and we had data aligned, but we had two sets of data points. These were for two different temperatures. So this means that temperature also has a strong effect. So we need to incorporate the effect of temperature in our model. This is another way to plot the data. So the strain rate is here, and here is the temperature. And what you see here is results of experiments. So here you have different sets of experiments. And what we can do is to enrich the power law model to include the effect of temperature. This is done by using a Arrhenius fit. So the fit parameter here will be H, and the new variable is T. The gas constant R is simply a constant, so it's not to be fitted. So the power law relation is modified by introducing the exponential of minus H divided by RT, H to be determined by fitting the diagram. So what happens is that an increase of temperature decreases the stress in general. This will have very important effect for the rheology of the lithosphere, because as temperature increases with depth, the viscous flow stress will exponentially decrease. These diagrams, they show you distribution of differential stress with depth for oceans and continent. The different sides is for compression and tension, compression and tension. What you see is basically that in the oceans below a depth of about 40 to 60 kilometers, the part here, which is with a straight line, it shows you the brittle regime. Below is the viscous plastic domain, and in this viscoplastic domain, the temperature-dependent viscous creep dominates, and the differential stress in tension or in compression decreases exponentially. So here it's very weak. So at the base of the lithosphere, the stress is expected to be weak, and it's mostly an effect of the temperature-dependent creep. The same would apply to the continents. So strength reduces with depth, and this may allow plates to be decoupled from the asthenosphere. That's a first order effect of temperature on plates. Another effect is related to the conversion of mechanical work during deformation. So in fact, when permanent deformation is applied to a material, a large part of the mechanical work is converted into heat. And this heat will then reduce the local viscosity by a local thermal effect, which will enhance the strain rate. So you can have a nonlinear coupling between deformation, production of heat, and a temperature activated viscous creep. So what you see on this diagram is a result of a 2D experiment. You have a continent on that side. This is a continental crust with the orange color, and you have an oceanic plate on that side. It's being deformed, so mechanical work is applied, it's compressed, and you see an evolution through time. And you see at 8.7 million years, the line here is the 800-degree isotherms. It just peaks up here, and what's happening is that deformation is localizing, temperature increases, and this leads to the reduction of viscosity and the formation of a subduction zone. So the deformation localization, even at the plate scale, can be linked to this temperature effect of rheology. So this is a first order effect. Other effects on rheology can be the effect of water. So to take into account the effect of water, we can further enrich our power law model by adding the water fugacity here. So the water fugacity is a parameter that can vary but there is a fit that needs to be made with regard to experimental data. So you see here experimental data for quartz with the differential stress on the vertical axis and the value of water fugacity on that axis, and the fit allows to obtain the value of R. So that's the fit parameter. Another important effect in rheology is the grain size. So here are again experimental data that correlates the stress to the size of grains. In order to take into account the effect of the grain size, we can further enrich our model, our Paolo model, by taking into account d, the grain size, so that's the new variable, to the power minus m, and the minus m, or m would be the fitting parameter we want to extract from the rheological data. We can even go further and take into account the effect of pressure. So what we had in the exponential term before was h here, but h is actually E, the activation energy, plus PV, P being the pressure and V is the activation volume. So there is an effect of pressure on viscous creep, and it is included in this term. Again, in order to model the effect of pressure, so we have this new variable, we have another fit coefficient, and the fit coefficient is now the activation volume, which can be deduced from laboratory measurements. So, since we discussed about viscous creep of rocks, you may have heard about dislocation creep. So dislocation creep is one deformation mechanism which results or which causes effectively a Paolo behavior. It's related to the motion of dislocations inside crystals. It is sensitive to stress, hence the Paolo effect, and also temperature. So in this picture you see a microphotograph of quartz in which there are dislocations, black lines, also fluid inclusions, gray circles there, and you see here in addition a high density of piled up dislocation which lead to the creation of a new subgrain boundary. So what's happening in dislocation creep? We start from the left side of the picture. You have a dislocation indicated by this symbol here, and this is a lattice of a grain. This black line is a passive marker. It's the black lattice plane here. Simple shear deformation is applied to this lattice, and the dislocation is migrating inside the grain. As the dislocation migrates, it will go through the passive marker and it will offset the passive marker line. So as the crystal is being sheared, the motion of the dislocation causes the offset of lattice planes. So that's typically the cause or linked to Paolo exponent larger than 1. Another type of deformation mechanism you may have heard about is the diffusion creep. So the diffusion creep is linked to the solid state diffusion of vacancies through the lattice. It's sensitive to temperature and grain size. So in this sketch you see a grain which is being deformed in tension, so it changes from a square here to a rectangular shape, and the lines are indicating directions of atom diffusion. So what can happen is that here we have a crystal boundary. This is again the lattice of the crystals. As the crystal is being stretched and the vacancies are diffusing through the grain, you can stretch the crystal and include new vacancies inside. This type of creep is expressed with this type of flow law here, where you have the stress to the power n and d, the grain size, to the power minus m. But for diffusion creep, usually n is about 1, this one, but m is larger than 1. So, in fact, the diffusion creep, if we remove here, if we leave apart the effect of temperature, is simply this law here, tau to the power n and d to the power minus m. N is 1. So one may think that this is a linear creep flow law. But don't forget that m is 2. And in fact, m, the grain size, depends on the deviatoric stress via paleopiezometric relationships, which are also calibrated in the lab. So that's an expression for d as a function of stress. We have b, tau to the power minus q, and q is usually on the order of 1. So if we start with this expression and introduce d equal b tau to the power minus q in this expression, we obtain these terms here. Let's cluster the terms. So we put c and b to the power minus m together, and we get tau to the power n plus q m. We call this term c effective, and we call this term n effective. So what this shows us is that even a diffusion creep with an n of 1, because m is larger 1, or even larger than 0, it becomes effectively a power law flow law. So that's an important message here, is that even apparently linear flow laws dominated that represent diffusion creep are in fact power law. So they have a power law behavior. So as a conclusion, the viscous creep is related to grain scale deformation mechanisms such as dislocation creep or diffusion creep, but there could be also other mechanisms such as pressure solution, pyres, cavitation, grains, boundary sliding. But all of these mechanisms, they can be represented by a power law flow law, or even an effective power law flow law, as we did on the previous slide. And this power law model is so very useful, and it can be enriched to include other effects, such as the effect of temperature, which is a first order effect on viscous creep, grain size, pressure, or water fugacity. So we have seen how to enrich the model here. And yes, the power law is a very powerful model, and I leave you with this statement that this is the power of the power law flow law.